Welcome back to Advent of Code 2021. We're on to day 13. Halfway. Day 13, Transparent Origami. You reach another volcanically active part of the cave. It would be nice if you could do some kind of thermal imaging so you could tell ahead of time which caves are too hot to safely enter. Fortunately, the submarine seems to be equipped with a thermal camera. When you activate it, you are greeted with, "Congratulations on your purchase. To activate this infrared thermal imaging camera system, please enter the code found on page 1 of the manual." Apparently the elves have never used this feature. To your surprise, you manage to find the manual. As you go to open it, page 1 falls out. It's a large sheet of transparent paper. The transparent paper is marked with random dots and includes instructions on how to fold it up. Okay. Oh, it's a... Ooh, interesting. It's a folding problem of some sort. Okay. The first section is a list of dots on the transparent paper. Yeah, 0, 0 is the top left. The first value, yeah, blah, blah, blah. Yeah, okay. Hash is a dot, and dot is an empty, okay. And then there is a list of fold instructions. Each instruction indicates a line on the transparent paper and wants you to fold the paper up or left. So basically the dots merge. Okay, okay. Notice, for example, the 2 dots in the bottom left corner before the transparent paper is folded. After the fold is complete, these dots appear in the top left corner. Yeah, I get it. The transparent paper is pretty big, so for now, focus on just completing the first fold. After the first fold in the example above, 17 dots are visible. Dots that end up overlapping after the fold is completed count as a single dot. How many dots are visible after completing just the first fold instruction on your transparent paper? So we don't even really need to store the whole grid. You just need to know where the dots are, really. As a hash set, because it's like when you fold, it's a projection from this grid to a smaller grid. The ones that are in the top half will stay put. The ones that are in the bottom half will go to the top half. So basically you're projecting, which will reduce your dots. Well, no, it won't reduce them. They could stay the same. You could have the same number of dots, just different positions, but it's projecting onto a smaller space. So we don't actually need to store the whole grid here, like all the empty spaces. We just need to know where the dots are. It's literally just a hash set of the dots. How many dots are visible after completing just the first fold instruction on transparent paper? Okay. Seems Seems easy. And part 2, I don't know what could really be complicated. They might ask us to do it 100 times or something. Just do all the folds. If we can do one fold, we can do many. Okay. So, hello DJ. Doing an origami problem. So we have a bunch of dots on paper, which we need to extract. And then we need to fold the paper along these lines. Yep, I just started, so are you ready? I mean, this seems not too difficult. Folding, so if we've got a bunch of dots on a piece of paper and we fold the paper, basically the dots that, if we're folding the bottom half of the paper up, then the dots that were already in the top half will just stay put. And the dots that are in the bottom half will basically reflect along the folding line. So, wait, if we fold along x equals 655, then what about the dots that are on exactly that line? I think they just stay put as well, don't they? Will they get destroyed? Let me look at the description again. I think we destroy the dots that are on the line. Yeah, because that line just disappears. Interesting. Fine. Maybe they've made it so that there's no dots along the fold lines. Because they didn't give any example of a dot being destroyed. So we just have one big example, one sheet of paper basically. So I guess we want dots. We could just make it a hash set. And wait, why are we making a hash set? Because if two dots exist in the same place, then they are just the same dot. So we're making a hash set to remove duplicates. And for each line, so let's say if comma in line, that means it's a pair. So we just say x, y equals there's also one blank line, so if it starts with fold, then so axis is going to be position 11. And line and the position will be basically the int of whatever's left. So right now, we just want to do one fold. Let's write a fold method. So if you fold a set of dots along an axis, which is going to be a letter X or Y, and position of the axis, I suppose, then we want to basically create a new set of dots. And then for dot in dots. All right. So the code looks different if it's horizontal or vertical. Can we write it in a way that it doesn't... Yeah, so basically axis, so we'll say index equals, so the first parameter is the x, and the second parameter is the y, in the way that we've done this. So for dot in dots, if dot index is less than position, that means it's, so if it's horizontal, it's above. If it's vertical, it's to the left. Either way, it stays put. So we put it in new dots. Elif is greater than pos. We have to do the reflection, so it's so it's okay, hang on. How do you do a reflection? So you translate to the line x equals 0 or y equals 0. Then you do negative, because that flips it. And then you translate back. That's how you do a reflection, formulaically. So it's going to be... So the reflected value will be... It's going to be dot index, so minus pos, that just moves everything to the origin, and then we do minus, so actually it'd be pos minus dot index. And then we add pos back. We'll move it back. So it's basically 2 times pos minus dot index. Is that right? Yeah. It's the other way of thinking of it is if you put another line that's like the same distance ahead and came backwards, you would end up just over the line. It's easier if I draw it on paper, but I think that's correct. So that is the new index. So we have to say reflected pos equals none. Just make this a list for now. So reflected pos index is going to be 2 times pos minus dot index. Okay, that's reflected. And reflected pos I mean, we could just say equals list dot. It's just a copy of dot, but we changed the reflected axis. And then new dots dot add tuple reflected pos. That's a fold along the axis. I think that's right. So for part 1, we just say the very first time we do a fold, we say we do the fold. If part 1 equals true, just now print the length of dots and don't do that again. So we're going to do all the folds anyway. And if they're on the line, I guess they get destroyed. So that, yeah, that's covered. Got to split on the comma. 607? Is that what they asked for, the number? How many dots are visible? Okay. Correct. Finish folding the transparent paper according to the instructions. The manual says the code is always 8 capital letters. Oh, it's a visual thing. Okay. What code do you use to activate the infrared thermal imaging camera system? Fun. We have to print it out. So then, let's just say, height equals max dot add 1 because we want, and get the width. Just say grid equals let's make a grid, and then for dot in dots grid height, no, grid dot 1 dot 0 equals hash. And now for row in grid print. All right, let's see what this looks like. Oh, you have to really squint, but it's CPZLPFZL. CPZLP. Has to be right. Like, I've yet to see an example where he's made it where if you do an obvious wrong thing, you actually get a completely different message, but completely intact and realistic looking message. That would be hilarious, but I've never seen that happen yet. Like basically swap Z. If you swapped the X and Y axis, well, no, then it would just be mirrored. All right, that was a nice, easy problem. I can see how people would be scared of that problem because it looks like it's using spatial awareness or something, origami. I mean, we've had origami problems which required so much spatial awareness that most people actually had to go. There was one infamous problem which involved moving around on the sides of a cube. And like if you go round the edges of a cube, you appear on certain faces, but you start with a template of the cube, like before it's folded up. So, and you're trying to work out walking around on this template where you would end up on the cube. And I didn't think you really needed to make a physical cube. I did, just for the fun of it, but a lot of people really needed it. So they made a physical cube out of paper, cut it up, folded it up, and then they were able to calculate which edges touch which edges, to work out where you would end up if you're walking around on this cube. So that was cool. A lot of people were posting photos of their cubes. I should have kept mine. I didn't have like glue and stuff to actually wrap it up properly. It was just kind of, I was holding it with my fingers. But yeah, this problem doesn't, it's just a reflection in the axis, so. All right. Day 14. Extended polymerization. Oh, it's a polymers problem. He likes his polymers problems as well. These usually are like, what are they called? Like regular expressions? No, not quite. Automata? Yeah, it usually delves into the area of automata, which is a very interesting theoretical computer science field, and it's one of the first things you learn before you learn what a programming language is and why it even works. So it's important stuff, but it's a lot of theory that you eventually forget, and tends to be something you never address again because, you know, now that you've established programming languages exist, they work. You don't tend to need to go back to this theory, but it's interesting stuff. I mean, the reason we care is because we want to know that a computer can interpret a program in one and only one way. If it can't, then it's a failed language. Like, you can't have ambiguous languages. So the automata theory sort of comes along with theoretical results which prove that under certain conditions there can be only one way to interpret a section of code. And that is what is known as context-free grammar. Alright, well, the incredible pressures at this depth are starting to put a strain on your submarine. The submarine has polymerization. I wonder if there's actually quite an intersection between the chemistry side of polymerization and coding. Probably. Equipment that will produce suitable materials to reinforce the submarine, and the nearby volcanically active caves should even have the necessary input elements in sufficient quantities. The submarine manual contains instructions for finding the optimal polymer formula. Specifically, it offers a polymer template and a list of pair insertion rules. Okay, so it's 2 characters to 1 character. A rule like AB to C means that when elements A and B are immediately adjacent, element C should be inserted between them. These insertions all happen simultaneously. So starting with the polymer template NNCB, the first step simultaneously considers all 3 pairs. The first pair NN matches the rule N to C. So element C is inserted between the first N and the second N, okay. The second pair NC to B, so B is put there, and then H is put there. But it happens simultaneously, which is maybe the tricky bit. So you can't do them one at a time, because then you mess up the indices. Like, if you were to... Well, it wouldn't really mess anything up. But you got to make sure you're not looking... Like, if you put a C in there, you can't then do NC. Because that's from a previous step. So you... Guess you have to... Like, just make a list of all the insertions you need to make before you make them. And then do them. Okay. Fine. Thinking a bit ahead here. Note that these pairs overlap. Yep. Polymer grows quickly. 7 blah 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 blah. So after step 5, it has length 97. After step 10, it has length that. After step B occurs that many times, C occurs that many times, H occurs that many times, and N occurs that many times. Okay. After 10 steps, interesting. I wonder what part 2 is going to be. Is it going to be something crazy big and we have to be really smart? You can't really break it up into fragments because the borders, but the gaps between the fragments that's a pair, so it's not an independent problem. So you can't really break it into independent sub-problems. But then if you find pairs that don't belong to this list, then they would technically be... No, they wouldn't. Yeah, so if you had... Like, if you found a... I mean, do we have every possibility here? We've got CH, HC, BH... HHNN, CC. It looks like we have every possibility. In that case, that idea goes out the window. Anyway, if we do it 10 times, I think it'll be... interesting. Alright, so... Okay. Okay, so... So polymer... So they have the template. Okay, so template equals f.readline dot strip, and then just fetch the empty line, and then from whatever's left, we've basically got this. So we've got what do they call it? Pair insertion rules. Okay, we'll just call it rules. Wait, how do they do it? So, saying yeah, all right, so I think first we just want to decide what we're inserting and where. So every pair should exist as a possibility, right? Should they? How many have we got? 2. We've got 100 rules. That doesn't sound like it's a complete set. Like it would be a power of... No, it wouldn't be a power of 2. It would be the number of letters. Choose two. So, do we have... I mean, either way, we could write it. All right, so we need to find what. So let's call it expand. So, okay, so we've got a new... Okay, so first we just have to decide what the insertions are and where, and put them in a list. Okay, so let's just make a list of pairs. It's going to be like the index and what to insert. So for -1 because the last item doesn't have a following character. So pair equals s I to I plus 2. Yeah, and then if pair, we'll check if it's in the rules. Then we are saying we have to insert. So the index we insert in is I plus 1. But this isn't... Hang on. This index isn't... So either we keep track of an offset or we start from the end of the list and work backwards. That wouldn't work either. I think we'll use an offset. So we needed a... If we've inserted a character, then everything is going to be offset. So it starts with 0. So it's going to be I plus 1 plus offset. And because we've inserted a character, that means from now on, wherever we look, well, this is confusing as heck. Couldn't you just make all the pairs, then insert, then recombine? I'm not sure what you mean, but I mean, there's different ways that we could do that, but I could just create a essentially, yeah, I think. Hang on. Okay, don't worry about this offset. We say new. Just call it temp. So yeah, so we've got, let's say, so we're looking at fs, and we know we have to insert something in between. So on the list, we'll put f. We'll put the thing that goes in between. And nothing else. And then we move on to sk. And then we do that. We'll put in the s. We'll put the thing that goes in between. And the k. Yeah. Then there's no issue there. Yeah, we don't need to deal with this. So ImRange. So for each pair, we just put the first of the pair and the middle, but not the end. And if we do that, should be fine. And then, of course, we have to add the last character. So for ImRange length, pair. So we always put that character in, the first of the pair, and then we check if that pair is a rule. And if it is, then we put in yeah, this is a clean way to do it. So we just do that, and then at the end of it, put the last character, and then we return this all joined up. Yeah, I was overcomplicating it. I mean, like, break it into the FKKS, whatever, then add the extra letter, and recombine them so you don't have to worry about offsets for the insertion. Yeah, I guess that's what I'm doing at this point. So each stage of this loop is looking at first FK, then KS. Yeah, that makes more sense than worrying about offset. And the offset didn't even work anyway, because it would differ between the characters we keep and the characters we insert. All right, so that is an expansion. Let's try it out. Range 10. S, so it'll be so we do it 10 times. Let's see how big this gets. Okay, not too bad. All right, so so what do they want us to find? Most common element and subtract the quantity of the least common element. So it's just look at these counts and do the max minus the min. In fact, I think counter even has a function built into it to do that. Like you want the range or something. Most common. Well, that'll tell us what the element is. We don't care what the element is. Total. Maybe not. I don't know. But this is just max minus min. Two, 3, 6, 0. Correct. 40 steps. Oh dear. Oh dear. Yeah, there's no way we are storing this string in memory. Okay. Well, okay, so we have to break it into... So the interesting thing here is that like if we had just fs by itself and sk by itself, if we just did those like 10 times each, that would still end with the s, and that would still begin with the s, so they would overlap. So you would, if you worked out those problems independently, worked out what the resultant string was, then that's breaking it into subproblems, isn't it? And you just, that one s is duplicated, so you take that off. So really, it's just it's really just a case of solving the problem for fs, sk, bv, vo, oops, and so on separately, and then to get the final totals, you just have to subtract 1 for each of these in the middle letters. So the problem reduces to like being able to find the count for one pair. Now that's still going to be too big, but like it means once we know the answer to one pair, like if it comes up again, we already know the answer. We already know the count for it. But okay, let's think. We're doing it 40 times, so we can make some sort of recursive function. Time to turn the laptop into a space heater, maybe. So really, we want to just know how many pairs. So instead of this counter that I've done, I've counted how many times a single individual letter appears here. We actually care about how many times each pair appears. So like in this initial one, fs appears once, sk appears once, And for the most part, it doesn't matter what order we do things. Like if we found PP separately and KBN separately, we could add them all together. The only thing that matters is that C is at the end and F is at the beginning, which means they get counted once only. But everything else gets counted twice because it's always part of two strings. So if we knew how do we make this rigorous? So given a string, we only need to know three things about that string. Starting character, the end character, and the full count of all the pairs in there and how many there are. We don't need to know anything else. We don't need to know what order they come in because it doesn't matter really. Like if I were to swap FP, well, we could test this out. Like, well, no, because we would actually change things. We would actually change the pairs count. But if let's work under that assumption. So all right. I think I can sort of see how we'd write this. So we want a method that given a string we perform one step. So we need to know the start, the end, just the start character, the end character, and basically a dictionary of pairs and their counts. And what we'll return is the new pairs counts after a step is performed. Yeah. I think this works. And we can test it on this example. So if we know that it starts with a certain letter and ends with a certain letter, and basically a full count of all the pairs, that means the pairs list is just as big as 100, right? And each of these will have a count, an integer. So we'll return a pairs list of size 100. So it's just every step is only using like returning something of size 100. Nothing's actually growing except the values of the ints are growing, but that's fine. So yeah, okay. So we want a new pairs equals, let's say it's a fresh counter. So for pair count in pairs.values, so we've got so somewhere in this string we've got this pair. So if that pair is in the rules list, if pair in rules, then every instance of those pairs splits into whatever the rule gives us. So the left side will be pair 0 plus rules pair. The right side will be rules pair plus pair 1. So the new pairs left will increase by that same count as 1 for 1. And if it isn't, I don't know if this happens, but if it isn't in the rules, then that pair just stays intact. So you just say new pairs of the original pair plus equal count. So, and that's almost everything. So now we've basically added up all the pairs. So now we've wait, did the start and end characters actually matter here? No, they only matter at the very end when we're trying to yeah, they don't matter in this function. The start and the end will always be the same. All right. So that return, and then we return this new pairs list. Okay. So we've got this template. So we know what the start is. Start equals template 0. End equals template -1. So what we want is pairs equals counter. Is there a quick way to count the? We'll just do it like this: for I in range length template -1 pairs I to I plus 2. So that's each of the pairs. No. Count 1 for that. So now we've got our initial pairs. Then for that in range 40, pairs is replaced by step pairs. So finally, we know what the counts of all the remaining pairs, and now we want to just separate that into letters. So every letter is going to get double counted except the start and end. That's the point of knowing the start and end. It probably won't matter. Hang on. Yeah, no, that's right. Okay, so letter count is a new counter. Counters are great, they just make things easier. For pair count in pairs. So each of the individual letters just gets added in. Okay. But everything's been double counted. And now so just to be absolutely correct, we have to hang on. And still confused about what to do with the start and the end. Okay, so basically we've double counted every letter in the middle, but we've correctly counted the one letter at the start and the one letter at the end. All right. Yeah, because there was no pair preceding the first letter and there was no pair after the last letter. So I think the easiest way to resolve this is just letter count the start character, just take that out. So it's going to be probably an odd number. because everything was double counted, but the first character is counted once because there was one pair which had it, but there was no pair before which had it. So this is an odd number. Take that out. Take this one out as well. Right? And now we halve everything in the counter. So for pair in pairs, this gets rid of all the double counting. Those should be even numbers. And now we put back in the start and the end. I don't know of a cleaner way to do this. Like, the numbers might be so big that this extra start and end doesn't matter, but this is... Oh no, it will matter because they're asking us for the exact quantities. Well, of the most common element and least common element, but it could be F or it could be F or C. We'll find out. And then we just have to do this. But that has to be done 40 times. We didn't... Oh no, we did. Yeah, so that's there. Just separate this out. Alright, we'll try it. That's the wrong word there. String index out of range. Pair count in pairs.items. Let me check I've got the right pairs here. For some reason I've got a single character in here. I think I've done the indices wrong. What? It's not supposed to be like that. For age pairs template. Ah, that should be I+2. So SKV over... Yeah, so it's one of each. Two of these. Okay, good. That number? I mean, there's so many things that could have gone slightly wrong here, but I think the gist of it is correct. No, it's too high. All right, now we have to figure out. Um, um, I mean, we should test it on our example here because this process will work. We don't have to do the step process anymore. Let's encompass this all as a method. Define get final counts for a given template and a given number of steps. And here we basically do all of this. That gets us the final count. Part 2 counter equals okay. So in theory, we could use this for part 1. So if we do 10, that's what they asked for. 2360 is what we got before. 4720. It's exactly double. Why have I got exactly double? So we halved the numbers there. Oh, what? No, this is the wrong counter. We're counting, we're halving them. We didn't halve them, basically. But can I not just do this? Am I allowed to do this? Yeah. Yes. Okay. So 40. So it's half. Oh, sorry, I didn't have the IDE visible. So basically what happened was this line was wrong. I was halving the pair counts instead of the letter counts. So we have basically exactly half of what we had before. Correct. That was an interesting problem then. And if we go back to the code, we can now just use that process for part 1. We don't have to we don't need an expand method because that's inefficient. Just say it's this, isn't it? Just expand. Yeah, we don't do this anymore. Yeah, there we go. So it really came down to knowing that order doesn't matter. Like, you have a pair somewhere in the string, it will end up as 2 pairs. And it doesn't matter where they are because everything happens, insertions happen inside a pair. So it becomes basically a series of fully independent problems, with one exception. The first character and the last character might be slightly off, but I mean, let's actually print final counter. Like, we probably got lucky, and the F and the So this is the final count. So like F 1619. So the start character F and the last character C. So C was not the biggest and F was not the smallest. So it didn't matter. Literally just knocking one character off, but it's completely but if F or C were the most or least, then it would matter because we'd be off by one in this answer. Unless both F and C. Unless one was the biggest and one was the smallest, then they'd cancel out. That'd be a bit funny, but yeah, it's mostly just if you have this many of this pairs, then next turn you'll have this many of this pairs. And every pair splits into two pairs. That's cool. Yeah, that's a good problem. All right. Can go for one last one. On to 15. Well, yeah, we'll go for it. Hopefully it doesn't take too long. Hang on, I need to think if I don't want to start a hard problem, and we'll take a quick peek at the nature of the problem. Okay, I think it's a short problem. We'll go for it. All right, 15. Day 15, Chiton. That's the Chiton. Marine mollusks. Gumboot Chiton. Alright. You've almost reached the exit of the cave, but the walls are getting closer together. Let's just cut to the important stuff. The shape is square. Quick scan gives us a risk level throughout the cave, so it's going to look like a bunch of integers up to 9, I guess. You start in the top left, and your destination is the bottom right. Straightforward enough. Cannot move diagonally. This is just a Dijkstra problem right now, isn't it? So you add up the risk levels of each position you enter. Okay, so you can think of it like distance. There's no reason to ever backtrack. Find a path with lowest risk. What is the lowest total risk of any path from the top left to the bottom right? That is just Dijkstra. Should be linear time in the number of cells. All right, let's remind ourselves how to go Dijkstra. The number of times I've done breadth first search, depth first search, Dijkstra, A star, and I know I could have so easily just stored those programs so I never have to write them again. But it's good practice, isn't it? Okay, so let me just put some more coffee on. Alright, so yeah, it's just Dijkstra. I don't see any tricks to it, and it's nice small numbers. See, I was storing my coffee in a packet that I previously stored my marijuana in, so I think the coffee's gonna be a bit weedy. Um, Alright, so it's the standard stuff for line in f dot read line grid dot strip. Do we want store it as ints? Yeah, might as well. Grid dot append. It'll be int x for x in line dot strip. Alright, so that's the grid. We know it's square. Just say width. Width equals length of grid. And then we want to define Dijkstra. So we're given a start, a goal, that's it. Just get my coffee. All right. So, when you do Dijkstra, you want to do priority queue. What do we use for that? We use the thing called priority queue. Isn't there another one that people suggested that's maybe better? Oh no, that was for the queue data structure. Hello, Smab UK. Did I make it before the end this time? Yes, you did. I just starting problem 15. I just did 13 and 14 now. They were both interesting problems. 13 was the one about you have dots on a piece of paper and you're folding the paper like horizontally and vertically, and the dots like combine or whatever. Pretty easy to code. And then 14 was 14 was a good problem. It was where you had a polymer, which is a series of letters, and it has expansion rules, so every pair has a rule for a character that gets inserted between them, and you have to count what the massive chain would look like after 40 steps, so you need some sort of counter process because the number is too massive. Oh, like I've still got the results down there. Yeah, that's how many letters the final result has. Didn't take me long to code because I guess I've seen similar problems in the advent of code. He quite likes these polymer questions, doesn't he? We've had a few of them. So there are a couple of tricks that are often used. It's mostly just keeping track of the count of the pairs, and that's the only thing you ever keep track of. Because then that's just a fixed size counter. Yep, we're on to 15, which looks like just a basic Dijkstra warm-up. So, probably want a queue. How many times have we coded this before? Not as many as BFS or DFS, I suppose. We could even make it A star. I won't bother. It's going to be fast enough on this grid. Q equals, and it probably won't be that effective either because the estimate will be like 1 for every step, but clearly this is like going to be way more than 1 most of the time, so I don't think A star is even that good. Well, it would be decent because it would still keep us going to the bottom right. Alright, so Q, priority Q, and then we want Q dot put start. So you start with the values. It's going to be 0. Start. Just check by solution. Definitely use Dijkstra. Yeah, I mean you can't really do it without Dijkstra. Like I'm sure people might have come up with their own solutions, which were really just Dijkstra without, like, they may have just basically invented Dijkstra from first principles, which is not too hard. But it may not use the same data structures and stuff. Yeah, I've written this so many times, and I could easily have just stored Dijkstra in a library somewhere, so I wouldn't have to write it so many times. But it's always good to just write it from scratch. Okay, what do we need? We need a visitor set. I suppose we actually want to have visited start. No, you only visit things when you expand them. That's the general rule. And then while q dot while not q dot empty. We do current equals q dot get. Now we have to. Now are we gonna do lazy deletion here? Yes. Oh yeah, we need a distance, don't we? Then we don't need a visited set. Our current distance equals q.get. So in the queue, we've got a node, and we've got the distance that we've used to get to that. Now, in the meantime, before we pull this out, we may have found a better path to that location, in which case we have to lazily delete this. So we say, if d is less than dist current, that means this is obsolete. So we skip it. Wait, it's a priority queue, so why would that happen? Oh yeah, because we would have computed that one before, but the slower, the longer path to it is still stuck in the queue somewhere. We don't have a method of efficient deletion. I think you can use hash sets to do that, but okay, so we're working with the best path to this current. All right, if current is goal, I think we are immediately done. This absolutely must be the shortest path. So return D. We're gonna have to get neighbors. So for di dj in all right, if 0 is less or equal to I is less than width and it's a square, we'll just assume it's always a square. Okay, so that's get neighbors. So for neighbor in get neighbors current. Okay, so neighbor dist equals d plus 1. If no. D plus grid neighbor 0, neighbor 1. It's the value in the grid. Are there zeros in here? No. It would still work even if there were. If they were negative, then that's the problem. You can have cycles and stuff. Neighbor dist d, so current distance plus the distance to enter that cell. So if neighbor not in dist or dist, what we previously found is worse than neighbor dist, then we found a new best. So we update that. So we update the distance to the neighbor, whether or not we've seen it before. We pop it on the queue. So it will be neighbor dist, neighbor. Is that everything? Yeah. And then if we reach this point, we shouldn't. But if we reach this point, it would mean we couldn't find a way to the goal. Leave that out for now. So let's just print Dijkstra from 0, 0 to I guess width -1, width -1. Go. Key error 0. Dist. Current 0? What? Oh, this is the wrong order. The current dist neighbor, yeah. We're out of range in the grid. So at some point we found a neighbor which was out of the grid. That shouldn't happen. Should be within these bounds. Because it's square, we don't have an issue with using the wrong axis. 1001. 01 was out of range. A grid. Oh, neighbor. What? Neighbor 1 is 1. Grid. Let me just print the grid, make sure I haven't kind of made it all wrong. Oh my god, what happened here? What? F.read line. I missed an S. F.read lines. 462. Correct. Now that you know how to find low-risk paths in the cave, you can try to find your way out. The entire cave is actually 5 times larger in both dimensions than you thought. The area you originally scanned is just one tile in a 5x5 tile area that forms the full map. The original map tile repeats to the right. It's a subtle bug, yeah, the most subtle of bugs. Like, usually I print my grid to start with just to make sure I've done it right. Full map. Your original map tile repeats to the right and downward. Each time the tile repeats to the right or downward, all of its risk levels are 1 higher than the tile immediately up or left of it. However, risk levels above 9 wrap back around to 1. So we can just build the full grid that's 5 times bigger. It's not going to be crazy big. Or, alternatively, we just have a function that returns what a location should be. And it's not too hard to compute that, isn't it? We just do an integer division of the row size, blah, 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 add that, and modulus. So it's just Dijkstra in a bigger map. Fine. Well, because the Dijkstra is already coded to a hard-coded grid, we could just make the grid. Like, how big is it going to be? 100, so it's going to go to 500 by 500. That's fine. And the runtime would be linear in that number anyway, even if we didn't build the whole grid. So we might as well just do it. So we'll need a new getNeighbors method as well. Or we just say for a given width. Try and avoid carrying forward any bugs. We'll just make a new getNeighbors. Dijkstra will be the same. Alright, it's actually better if we just supply a width. Or the grid. The width will be fine. Supply a grid, because we actually will supply... Yeah, actually this actually does make sense. Because then you can just say get neighbors, current, grid, dot, the grid, length of grid. So we're supplying the grid, and yeah, get rid of this. And then get neighbors. It's gonna be... There we go. And then get rid of width. Alright, get neighbors width. Width. Okay, and then Dijkstra uses a grid. And then here be make sure we still get the same result. 462. We should. Yeah, okay. Okay. So now we just expand the grid and then plug it back into Dijkstra. Bigger grid. Just so that we don't have to keep calling that. Bigger grid. It's gonna be. So it'll be. Let's say none. For 5 times width. 5 times width. Or we can even say bigger width equals, okay, big width. Big width, big grid equals 5 times width. Big grid equals that for I in range. Big width for j in range. Big width. So we want to know which phase we're in each. What did they say again? So it's repeats to the right and downward. Each time the tile repeats to the right or downward, all of its risk levels are 1 higher. So it's basically the number of phases to the right plus the number of phases downwards is the number of levels higher you go. Okay. So, num tiles. I don't know a better description, but num horizontal tile equals start with the vert equals I divided by little width. So it'll be 0 for the first one and so on. Okay. j divided by width. So the value equals, so it's going to be grid, going to be I, but modulo out all those widths. So it'll be the value that's in the original grid plus hang on, so it doesn't wrap around back to 0, it wraps around back to 1. So what we actually want to do is so you sort of minus 1 and then you do modulo 9 and then you add 1 back. Either that or you just divide by the number of, yeah, I think the easiest way to write it is just so it's going to be, so we minus 1, so that it's now a number from 0 to 8, and 9 means it goes back to 0. Right? Then we plus that and plus that. That's how many times it increases. So that number we want to modulo 9. So it goes back to a range between 0 and 8. And then finally add the 1 back on to bring it back into the 1 to 9 range. Yeah, I think. All right, value. That's the value of this one. So basically, big grid I j equals value. So we've stored all the values now. We don't have to do it on the fly. And now we just do this, right? We 0, 0. It's big. Oh, okay, that was quick. 2, 8, 4, 6. Could try throwing an A star in, but maybe probably can't be bothered. Correct. Yeah. I mean, if it works. If I was rewriting this bit of code, I would refactor into methods to explain what it does better. Looks weird reading it now. Could try throwing A star in, but then how much work do we have to do? It's just it's not interesting. It might be faster, but we'll save it for a time when we actually need that speed. Well, that went quicker than expected, so I could actually squeeze another problem in. I'll take a peek at the next problem. Bloody hell. Okay, there's already a lot of reading. It may well not be that complicated, but I'll leave it till next time. Yeah, alright. Gonna go get some dinner then. And So that's coming up to 2/3 of the way through. Seems easy compared to other years. Yeah, I don't think there was anything really tough. Like that origami thing reminded me of the infamous cube one, where people had to literally make a cube out of paper, like cut out a template in real life and stitch it together to be able to figure out how to solve the problem. You didn't have to, but it helped a lot. And everyone was posting photos of their cubes. Which year was that? I think it was like maybe 2022? I don't remember. So the stats... yeah. 16 might be a little harder, I don't know. 19 looks like it might be the hard one. And 21 might... Can't tell whether that's easy or hard. Well, a fewer percentage actually solved it, both parts, but more people attempted it. I don't know. Alright then. Don't think anyone is ever really doing Advent of Code nowadays. Let's have a look. Code. Someone's doing 2022. Okay. Well, that's it. Thanks for watching. Probably unlikely to be doing this tomorrow. Probably in a couple of days' time. Alright, catch you next time. Bye-bye.